Very good morning. Welcome you all to the online STTP on Bloom's Taxonomy, Higher Order Thinking Skills in Electronics and Communication Engineering. And this is our last module of this STTP. And this module is about control system. Myself, Mr. K. Arun Kumar, working as assistant professor in the Department of ECE, Savita Engineering College. Today we are going to discuss about most of the gate control system papers. We will start with the first question. Question number 1. In the feedback system shown below, they are given some g of s, that is transfer function of the system. That is nothing but 1 divided by s square plus 2s. The step response of the closed loop system should have minimum settling time and have no overshoot. Okay, and they are given some closed loop closed loop system. For this system, what is the required value of gain k to achieve minimum settling time and no overshoot? Hope you understood the problem. They given the open loop transfer function g of s, that is 1 divided by s square plus 2s with order 2. They are going to achieve minimum settling time and peak no overshoot. If that is the case, what should be the value of k? Okay, and this is a negative feedback. So now we'll find how to find the value of k for this problem. Okay. So whenever we are trying to achieve minimum settling time and no overshoot, that is nothing but critical damping. Okay. I think we all know for the second order system, damping ratio, if it is equal to 1, I can say it is critical damping. If it is greater than, I can say it is over damping and under damping and so on. So, okay. And whenever we're trying to achieve minimum settling time and no overshoot, we should go for critical damping. For critical damping, the damping ratio should be 1. Okay. Since they given the second order system, and we all know the closed loop second order transfer function is nothing but g of s divided by 1 plus g of s into h of s. G of s they mentioned in the problem. H of s nothing but it is a unity feedback gain. Here you can see this is a unity feedback gain. So we can take h of s is equal to 1 and g of s is equal to k divided by s square plus 2s. Now substitute in the transfer function, that is closed loop transfer function formula, and try to obtain y of s by r of s. So here I am getting y of s by r of s as k divided by s square plus 2s plus k. And we know the well-known formula for the second order system. For any second order, the transfer function should be in the form of omega n square divided by s square plus 2 epsilon omega n into s plus omega n square, where omega n is nothing but natural frequency, epsilon is nothing but damping ratio. By comparing the standard form with this obtained form, I can say that the coefficient of s is 2 here. So the coefficient of s is 2 epsilon omega n here. So I can compare this to, so 2 epsilon omega n is equal to 2, then 2 epsilon omega n is equal to 2. Okay. Since it is for critical damping, epsilon is also 1. Okay. Substitute that epsilon is also 1, then I'm getting natural frequency is equal to 1 radians per second. But the question is not omega n, they're asking for the value of k. Okay. Once again, by comparing the constant alone, here it is k, here it is omega n square. So omega n square is equal to k. So then k is equal to omega n square. Then the value of omega 1 we achieved is 1. So that you can substitute here. So the value of k is equal to 1. Okay. Now this is the answer for the given problem. Yeah. So once I explain you, the given open loop transfer function, they are asking the closed loop transfer function. The transfer function, the system should have minimum settling time and no overshoot. To achieve minimum settling time and no overshoot, the damping ratio should become 1. That is nothing but critical damping. So after finding closed loop transfer function, compare with the standard format and find the value of omega n and epsilon and equate it, you will get the value of k. Okay, this is the first one. Next, in the feedback system shown below, g of s is equal to 1 divided by the given 3 poles or 3 factors, s plus 1 into s plus 2 into s plus 3. And they given again closed loop transfer function, closed loop system. And what is the positive value of k for which the gain margin of the loop is exactly 0 dB, as well as the phase margin of the loop is exactly 0 degree. If that is the case, what will be the value of K? Okay, that is the question. Once again, try to understand this. They given open loop transfer function G of S and unity feedback gain H of S is equal to 1, and they're asking the value of K when the gain margin is 0 and phase margin is also 0. Okay, and this is a very important one. When the gain margin and phase margin are 0, then it represents marginally stable system. Okay, when the gain margin and phase margin both are 0 dB and 0 degree, then that type of system represents, that type of system exhibits only marginal stable. So I think we all know how to find the stability of the system. Okay, that too we are talking about continuous time system. So we should talk about the Laplace transforms. So the stability of the system can be described or can be delivered with the help of poles locations. If the poles lies on the left side of S plane, if all the poles lies left side of S plane, I can say the system is stable. If any one of the poles lies on the right side of S plane, I can say system is unstable. Instead, if any of the poles lies on the imaginary axis of S plane, then that type of system is said to be marginally stable system. Okay, when the gain margin is 0 dB and phase margin is 0 degree, such type of systems exhibits marginally stable system. So the given GFS, that is open loop transfer function, is given. So we can able to find the characteristics equation, that is nothing but your denominator of your closed loop system. Okay, the characteristic equation is given as 1 plus G of S into H of S is equal to 0. GFS they given, that is nothing but S plus 1 into S plus 2 into S plus 3, K divided by and so on so. And H of S is 1, so substitute both the things and try to find out 1 plus GFS into H of S. So here I am getting 1 plus GFS into H of S nothing but S cube plus 11S square plus 6S plus 6 plus K is equal to 0. So they ask me the value of K, and I know that marginally stable. When we are talking about the stability, then directly I can go for Routh-Hurwitz criteria. Okay, the R is RH stable simply. Okay, since the maximum order is 3, so I can start with S power 3 and S power 2. In the first row, locate the values of S power 3, that is odd power terms. So this is a coefficient of S power 3 and this is a coefficient of S power 1. Okay. In the second row, that is S power 2 row. So the first element should be the coefficient of S power 2. The second element should be the coefficient of S power 0. That is nothing but constant. Now to construct S power 1 row, okay, so always follow this. To construct S power 1 row, cross multiply this and cross multiply the second term and do the subtraction. Okay, here 11 into 6, 66 minus 1 into 6 plus k, that is minus of 6 plus k, which is nothing but overall 66 minus 6 minus k. 66 minus 6 is 60, 60 minus k whole divided by the first term. This is RH, row construction. Okay, 11 into 6 minus 1 into 6 plus k whole divided by 11. So I am getting 60 minus k by 11. Now similarly you can proceed for next row also. To construct S power 0 row, once again do the cross multiplication. 60 minus k by 11 into 6 plus k whole divided by minus 11 into 0 whole divided by 60 minus k by 11. Both 60 minus k by 11 will get cancelled, so only the remaining is 6 plus k. Okay, now see the first column. So the first column is nothing but, I think so clumsy. So the first column is nothing but 1, 11, 60 minus k by 11 and 6 plus k. Okay, and we know that the first column of RH table should have positive values to be a stable system. If any one of the value is negative sign, then I can say the system is unstable. Instead of positive and negative, if any of the element is 0, then I can say system is marginally stable system. Since the given input is marginally stable, so that should be any one of the elements should be 0 in the first column. Then 1 cannot be 0, 11 cannot be 0, and the third element is 60 minus k by 11 should be equal to 0 for a for a marginally stable system. Then 60 minus k by 11 is equal to 0. So 60 is equal to k, or k is equal to 60. The value of k is equal to system. Once again, I'll repeat this. They give an open loop transfer function. They're asking the value of k. That value we should find out when the phase margin is 0 degree and the gain margin is 0 dB. While satisfying these conditions, what is the value of k? That's they are asking. When for any system, if the gain margin is 0 dB and phase margin is 0, that system should be a marginally stable system. And we know this from the RH table. To get marginally stable, marginally stable system, any one of the element should be 0. Construct the RH table and try to equate to 0 and find the value of. So for this problem, I'm getting k is equal to 60. Next, question number 3. The asymptotic Bode phase plot of g of s is equal to s divided by s plus 0.1 into s plus 10 into s plus pole 1, that is p1, with k and p1 both positive. Okay, it is k divided by s1 into s plus 10 into s plus p1 with the k and p1 shown below. Okay, they given some Bode plot. What is the value of p1? Okay, this is a Bode plot for the given g of s. Now they're asking what is the value of p1. Okay, it is once again very easy. Now take the f s. Okay, so this is also k. Now take the g of s. G of s is equal to k divided by s plus 0.1 into s plus 10 into s plus p1. Okay, now since value of p1 and they given the frequency versus, they given the phase plot, frequency versus angle. Okay, so directly I can go phase plot. To get the phase, I think we all know a plus jb format. The phase is tan inverse of b by a equal to j omega in the g of s. Then try to obtain response. Omega 0.2 from the, so since it is in the denominator, we'll get the negative angle. So minus 1, this is for the first one, minus tan inverse of omega by 10 for the second one, minus tan inverse of omega by p1, which is nothing but your phase of the given g of s. Now we should know the value of this p of p1. To get this p1, we should know the value of omega as well as the phase. Now from the figure, we understood that at omega is equal to 0.1, the phase is minus 45 degree. Otherwise, at omega is equal to 1, the phase is minus 135 degree. This is we understood from the figure. Okay. Now take omega is equal to 0.1 and substitute here. Omega is equal to 0.1 and substitute here. Omega is equal to 0.1, the angle is minus 45 degree. So omega will become minus 45 degree when omega is equal to 0.1. Substitute in all the cases omega is equal to 0.1 and try to minimize this, and we'll get the value of p, poles value. Here I am getting poles is equal to 1. That is p1 is equal to 1. So tan inverse of 0.1 by 0.1 is tan inverse of 1. Tan inverse of 1 is nothing but 45 degree, and this minus 45 and this minus 40 will get cancels, then there are only two more terms that we will equate. Maybe some participants or some of your friends may have a doubt why we cannot go with omega is equal to 1 at minus 135 degree. Okay, this is also correct. So even we can take omega is equal to 1, nothing wrong. So since your tan function is discontinuous at omega is equal to 90, whenever we are exceeding angle 90 degree, it is not basic trigonometry, especially for tan functions. We should use some identities. Okay, so based on identities, we have to minimize the functions. So that time some of us may feel a discomfort. So better always go with less than 90 degree. Only if we don't have any other choice for less than 90, that time we should follow the identities. If there is a choice, always go with less than 90 values. Do not choose more than 90. Okay, since its tan function is discontinuous at 90 degree, so it is always easy for us to choose the value which is less than 90. Hope you understand. First, try to find out the phase from the given transfer function and substitute omega is equal to 0.1. At omega is equal to 0.1, the phase value is nothing but minus 45 degrees in the given plot, that too Bode plot. And try to find the value of P1. Next, as another important and interesting and frequently asked question most of the competitive exams, especially GATE and ISRO and TRB. The open loop transfer function feedback equal to K divided by S square plus 5. The value of K at the break of the feedback control system root locus plot is. Okay, they're asking the value of K, not the value of breakaway point. Okay, and there are two more problems we are going to discuss based on the breakaway point. Just look into these questions thoroughly. The open loop transfer function is given, which has a unity feedback. The transfer function is g of s is equal to K divided by S square plus 5 plus 5. What is the value of K at the breakaway point feedback control system root locus plot? Okay, first we'll find out the breakaway point. To find breakaway point, we know that dk by ds, that is the differentiation of k with respect to s, should be equal to 0. And minima concept similarly. Okay, so dk by ds is equal to 0. To get the of, always go for once again characteristics equation. We know that characteristics equation is nothing but 1 plus g of s is equal to 0. G of s here the given is K divided by S square plus 5s plus 5. Just substituted and try to find the equation. So here I am getting S square plus 5s plus 5 plus K is equal to 0. This equation I can able to find the value of K. K is equal to minus of x square plus 5s plus 5. Now differentiate this equation with differentiate this with respect and equate to 0. If I do the differentiation of s square, it will become 2s, 5s will become 5, and constant will become 0. Now equate to 0 and find the value of s. Okay, so I'm getting s is equal to minus 2.5. Okay, I'm getting only one value. Okay, if there are more than one value, we have to check whether it is a breakaway or break-in. Sometimes even that point cannot be a breakaway also. Okay, so here I'm getting only nothing but take away point. Yes, the value is minus 2.5. Now, see the question, they're asking the value of k at, okay, now they're asking the value of k at breakaway. Here the breakaway is minus 2.5. To get the value of k, once again, we should go for your open loop transfer function. The open loop transfer function is given as g of s, k divided by s square plus 2s plus 5. So try to take the magnitude and equate to 1. Okay, substitute s is equal to minus 2.5 in all the cases, and try to minimize. Since there is magnitude, even if it is minus, you can change into plus. So k divided by minus 2.5 the whole square plus 5 into minus 2.5 plus 5. If you minimize this expression, you'll get minus 1.25. So k by minus 1.25 is equal to 1. So k is equal to minus 1.25. Since it is magnitude, I can take positive value. There is 1.25. Okay. So for any closed loop transfer function, if they are asking the breakaway point, the condition is dk by ds should be equal to 0 to break. Based on the breakaway points, we can go for further informations that based on the problem. Here they ask the value of k. Okay. Next, the open loop transfer function is given by g of s is equal to k divided by s into s plus 2. For the peak overshoot of closed loop system to a unit step input to be 10 percentage. What is the value of k? The open loop transfer unity feedback control system is given by transfer function and the mention unity feedback, and peak overshoot is 10 percentage for a unit step input. Now they are asking the value of k. Okay, we know that the peak overshoot in of IFC there the peak is something about 10 by 100 is 0.1. Okay, now they ask the value of k, and you can look in given second order system. If it is second order system, we clearly knows the standard format also. So if I know the value of epsilon, I can able to find the value of k or omega, depends. So from this expression, I'm going to find the value of epsilon. Okay. So epsilon, which is nothing but 0.1, that is 10 percentage. So take the anti-logarithmic, take the logarithmic, sorry, take the logarithmic, that is exponential log ln. So 5 epsilon by root of 1 minus epsilon square is equal to ln of 0.1. Square on both the sides and square root and try to find out the value of epsilon. Okay. So here I'm getting f is equal to 0.59. So after this it is very easy. Now I'm getting x1 is equal to 0.59 g of s, k divided by s into s plus 2, and try to find out the characteristic equation, which is nothing but 1 plus g of s into h of s is equal to 0. Here g of s is equal to k divided by s square plus 2s. Then if I do the s, I get square plus k divided by s plus 2, multiply the s, nothing but s square plus 2s plus k equal to 0. And just now, before one or two problems we discussed, format is s square plus 2 epsilon omega n into s plus omega n square. Now compare this two equations to get the value of omega n. By comparing these two, by comparing the coefficients of s, so 2 epsilon omega n, and omega n square is equal to k, which will give omega n is equal to root k. So here we know the value of epsilon, and other two numbers are constant. Check it out. So root k is equal to 1 by epsilon. K is equal to epsilon square. Epsilon is equal to 0. That we found in the previous. You can take the should finally 0.86. Very simple. So they given the formula, sorry, peak overshoot value, which is nothing but 10 percentage. Take the peak overshoot to 10 percentage and try to find the value of damping ratio. Second order either k. Lastly, and a damped natural the omega is equal to omega n into omega n into root of 1 minus epsilon. In same frequency, we should be able to answer for all in answer for all questions. Okay. Only important information we need is damping ratio and undamped natural frequency. That is nothing but omega n. Okay. If these two informations are known, we can able to find settling time, peak overshoot, rise time. Okay. Any set of parameters we can able to find if you know these two parameters for the second order system. For this problem, the value of k is equal to 2.86. Okay. So question number 6. The transfer function of a LTI system is given as, okay. All the control system should be LTI system. That should have linear time invariant. So the transfer function of a LTI system is given as h of s is equal to 4 5s minus 2. The number of zeros, the right half of the S plane. Okay. Uh, uh, yeah, this is the number 0. You unloop transfer function. In a closed loop transfer function, 1 plus g of s into h of s is 1 plus g of s into h of s is nothing but your denominator. Characteristics equations are right. So g of s divided by 1 plus g of s into h of s. Nothing but your c of s by r of s. For this closed loop system, g of s is your zeros, 1 plus s into h of s is your poles. Okay. But generally, if you go for characteristics equation, which is nothing but 1 plus g of s into h of s is alone. Okay. That time I never consider this g of s. For this equation, 1 plus g of s into h of s is nothing but zeros, not a poles. Okay. Considering here it poles, while considering here it is 0, but both are same. Okay. So here they are asking number of zeros in the right half of S plane. It is very simple. Once again we can go for R table. Okay, try to construct RH table. So in the beginning I said the number of poles or the amount of the pole should lies on the left side of S plane to be a stable. If it lies on the right side of S plane, I can say it is unstable system. The number of chain changes in the first column will give the number of poles on the right side of S plane. Okay. So the given 1 plus g of s into h of s is given. That is nothing but 2 s power 4 minus 5 s cube plus 5s minus 2. So since they started with s power 4, so first row should have positive power, that is powers. Okay. S power 4, s power 2, s power 4, s power 2, s power 0. And this way s power 3, s power 1. Okay. Here s power 2 is missing, so the coefficient should be 0. Now it is well-known procedure. We can able to construct RH table for the s power 2 row, multiply and multiply this way, subtract this 2, divided by this minus 5. I am getting 2 and minus 2. So once again, if I put 0 in the s power 1 row, if all the elements in a row is 0, then we cannot able to proceed further rows. For that we should go for always auxiliary equations to construct the next row values. Here the auxiliary equation is 2s square minus 2 into s power 0. That is your auxiliary equation. To get the next value, to get the next row, differentiate this equation with respect to s. The differentiation of 2s square is 4s and differentiation of minus 2 is 0. Then obviously the next row element is 4 and 0. This is how we have to construct our next row when all the elements are 0 in a row. Then once again simply you can go for S0 row. That is as usual. Take the number of sign changes in the first column. Okay, here it is positive, here it is negative. One sign change. Here it is negative, here it is positive. Second sign change. Here is positive, here is also positive, no sign changes. Here positive, here negative, so there is a third sign change. So from the first column, we understood that there are three sign changes. It means that there are three number of zeros lying on the right side of S plane. Okay. So also I can conclude the system is unstable. So the maximum power is S power 4. So there will be four poles generally. Out of that four poles, three poles lying on the right side of S plane, one pole lying on the left side of S plane. If I talk about the stability of the system is unstable since three poles lies on the right side and one pole lies on the, and one of the important concepts that is auxiliary equation. And there's another clue for you. Auxiliary equations always appears in the even number of rows. For example, the auxiliary equation may comes in the form of s power 6th row or s power 4 row or s power 2 row or s power 0 and so and so. At any cost, 100 percentage auxiliary equations will not come in the odd power rows. For example, s power 1, s power 3, s power 5. In such rows, your auxiliary will not. Okay. Next. The unity feedback control system shown in the figure. The open loop transfer function is given as 2 divided by s into s plus 1. What is the steady state error for a unit step input? Okay. So 2 divided by s into s plus 1. They are asking the steady state error. To find velocity constant, positional error constant, velocity error constant, error constant, that is Kp, Kv, and K. So and the type. Now here consider this open loop. Find the type. Okay, here the type is 1. Okay, I think we all know how to. Type is nothing but how many poles are lying at the origin. Okay, how many poles are lying at the origin. If I look into this g of s, given g of s, that is 2 divided by s into s plus 1, only one pole is lying at the origin, pole is lying at minus 1, s is equal to minus 1. So the type of the system is 1. For example, g of s is equal to 2 divided by s plus 1. Then there is none of the poles are lying in the origin, so the type is 0. For example, 2 divided by s square into s plus 1. Now there are two poles lying at the origin and one pole lying at a, so the type is 2 for such a system. Okay. For us in the given problem, the type is 1. Then I can go for velocity error constant, that is K. Sorry. Oh, sorry. I think so. Yeah, unit step input. For unit step input, the steady state error constant is 1 by 1 plus Kp. Kp is position error constant, limit s tends to 0, g of s. So I know g of s that you can substitute s equal to 0. Then I'll get 2 divided by 0, which will become infinity. Okay. It's a even without solving this, I can say, whenever the type 1 is given, whenever the type 1 is given and unit step is given, then Kp should be infinity, Ex should be 0. Okay. Maybe instead of unit step, if mentioned instead of unit ramp, then your solution is different. 1 by Kv. That is a different case. Correct answer also. So whenever they given type 1 and unit step, the K infinity and the EF should be 0. Question number 8. The first two rows in a root are bit stable. For the characteristic equation of a certain closed loop control system is given as. What is the range K for which system is stable? Since the range is stable, column should have sign, not even 0. Okay, they are completely stable. It is not marginally stable. We should get the positive. Okay, and we know that to consider one Then we'll multiply these two numbers, 2k into 2k plus 3 minus 1 into 4. Okay. So here we should understand that is 2k into 2k plus 3 should have a number which is more than 4. Only then I will get a positive number. Since I am subtracting from minus, for example, if 2k into 2k plus 3 is 3, then I will get 3 minus 4 is minus 1. Then system becomes unstable. So the mentioned system should be stable. So the condition here I am getting is 2k into 2k plus 3 should be greater than 4, not even equal to 4. That is very important. If you put equal, that becomes marginally stable, not stable. Okay. 2k into 2k plus 3 should be greater than 4. Just multiply and try to get the quadratic equations and factorize this. See here I am getting k is greater than 1 by 2 and k is greater than minus 2. Any DC gain constant cannot be negative value. Simply you can neglect k greater than minus 2 if possible. Okay, so the other one is k is greater than 1 by 2. If k is greater than 1 by 2, k can be 1, k can be 2, k can be any number till it is infinity. So the range of k is 1 by 2 to infinity. That is D. Okay, k takes value from 0.5 to till infinity. Next, another interesting one. They given two differential equations where x1 of t and x2 of t are state variables and u of t denotes the input. If the output ct is equal to x1 of t, then system is controllable, observable, or not controllable, not observable. They are given four different choices. Okay, they are given two differential equations. They mentioned x1 of t and x2 of t are nothing but state variables, and u of t is your step input, and c of t your output. Okay, first we should able to form a state matrix. Okay. Through differential equation, I can write the state matrix. So the directly they given, we don't want to derive any state equations. Directly they given differentiation of x1, differentiation of x2. So we can write differentiation of x1 of t is equal to minus 2 x1 of t plus 3 u of t for the first one. For the second one, differentiation of x2 of t by dt is equal to minus x2 of t plus u of t. Okay. So there are two state variables. Then your A matrix should have 2 cross 2 and B matrix should have 2 cross 1. That is a column matrix B. So here if I see the first equation, I'm getting x1 alone. There is no element of x2. So minus 2 0. Then if I see the second equation, there is no value of x1. So 0 minus 1 into x1 of t, x2 of t plus here input matrix 3 and 1. That is second one. Okay, any state variable in the form of x dot is equal to ax plus b, ax plus b. So with the standard representation I can compare. So from this I understood that a is equal to minus 2 0, 0 minus 1, b is equal to 3 1. Okay, and the output equations, if I see the output equation, c of t is equal to x of t alone. Your output equation, output matrix is always a row matrix, it's not a column matrix. I should write in the form of a row. So there are two state variables, then I should have two elements, x1 of t as well as x2 of t. If I see this equation, I'm getting only x1 of t. So c of t is nothing, c matrix is nothing but 1 and x2 has become 0. So I wrote c is equal to 1 0. To get to check the controllability and observability of the system, I can go for Kalman's test. Okay, it's very easiest method to check observability and controllability. There are so many methods, but we are preferring Kalman's test to checking observability and controllability. To check controllability and try to find the determinant for the first column should be a B, the second column should be a AB. Okay, take the B element. What's the B element? B matrix here 3 and 1. Okay, so 3 and 1. The next element should be a AB. Multiply A matrix with the B matrix. A matrix always a matrix. B matrix is always a column matrix. The SLN will be always a column. Okay. So after multiplication of AB, I am getting minus 6 minus 1. Just bring that value and keep it here. find out the determinant of this. Okay, this is only for 2 cross 2 matrix. If they given 2 state variables, okay. If they are asking, if they are given more than 2 state variables, then we should go for 3 cross 3. Okay, then this will become B, A, B, A square B, and so on. So it depends. So here, since it is 2 state variables, I have chosen 2 cross 2, and I'm use only 2 element B and A, B. Okay, and place the B column and place the A, B column, and try to find out the 2. If I find the determinant is nothing but 3, if it is not equal to 0, I can say system is controllable. Okay, if it is equal to 0, system is not controllable. Okay, I'm getting not equal to 0, so system should be a controllable system. Then similarly for observability, once again to check the observability, I can go for Kalman's test. So the condition is C transpose into A transpose, and so on. So instead of B here, I will have C transpose. It's once again very basic method. So just multiply and find the determinant. Here I'm getting determinant is equal to 0. Then system cannot be observable. Okay. So the option is it is a controllable. It is not observable. Okay. So I think option is A. Next, 10. The forward path transfer function and feedback path transfer function of single loop negative feedback control system are given us. They given GFS as well as HFS respectively, and so on. So if the variable parameter k is real positive, then the location of breakaway point on the root locus of the system. Okay, it is entirely different from the previous one. Okay, in the previous problems, maybe 2 to 3 questions back, we have discussed about breakaway point. There, based on breakaway point, we found the value of k, but it is not the case. Here, simply they are asking the breakaway point. They are given GFS as well as HFS. Yeah. Once again, we know the condition to find a breakaway point. Always we should go for dk by dA should be equal to 0. Okay. Since the given HFS, we can go for the formula 1 plus GFS into HFS is equal to 0. That is characteristics equation 1 plus GFS into HFS is equal to 0. Substitute GFS and HFS. HFS is a 1 year. Then this is a final equation I'm getting. GFS 1 plus GFS into HFS is equal to 0. Okay. Now I should get the k value. Then keep k at the left side. Try to bring all other terms to the right side. So k into s plus 2 is equal to minus of s square plus 2s plus 2. Then k should have, k will be minus of s plus 2s plus 2 divided by s plus 2. And we know that we should differentiate and equate to 0. So since they are in u by v format, we should go for the differentiation formula vu dash minus uv dash divided by v square. After differentiate, equate to 0 and find the value of s. After differentiate and equate to 0, I'm getting s is equal to minus 0.58 and minus 3.414. I'm getting 2 points. So in the previous problem, I had only 1. So simply I say the breakaway point is that value. But here I cannot able to conclude directly, or I cannot imagine anything. Either minus 0.58 can be a breakaway or minus 3.414 can be a breakaway. It is not so. Okay. Even 1 point can be a breakaway, the other point can be a break-in. It depends on the root locus. Okay. So to get exact breakaway point, take these values of S and substitute back in the S equation. Okay. It's one of the toughest process. Without calc, you cannot proceed this, but anyhow, okay. Logically, you can think and act. So first take the value of my S is equal to minus 0.58. Okay. Since it is S square plus 2 divided by S plus 2, and there is a whole negative sign. If I take S equal to minus 0.5, 0.5 whole square is 0.25, and 2 into minus 0.5 is minus 1, and plus 2. I am getting positive at the numerator. Similarly, if I substitute in the denominator, I am getting once again positive. Positive by positive is positive, and there is a whole negative sign at the front. Negative. So one of the way to check the value of key. If not, we can use calc. It is up to the participant's choice. So if I take s is equal minus 0.58, k is negative. If I take s is equal minus 3.414, k is positive. So why in the sense? So the numerator will become positive. Your denominator is negative. This negative and this negative will give the positive at the end. Okay. So for s is equal minus 0.58, k is negative. For s is equal minus 3.414, k is positive. Okay. For which value of s k is giving positive, that point breakaway point. Okay. Here s is equal minus 3.414 gives the positive value for k. So obviously s is equal to minus 3.414 can be a breakaway point for the given closed loop system. Then what about the value of s is equal minus 0.58? There may be possibility even there cannot be a point at anywhere in the root, or in some cases it can be a break-in point, but it is not our objective at this point. Okay, so only s value should give the positive value for k. Okay, out of this two, minus 3.4 is giving positive value for k, so I'm choosing that as a breakaway point. If both are negative, if both are positive, that time we have to look into it. Okay, so if both are positive, that time break in point will come to the picture. Okay, this minus 0.58 cannot be a break at any break in at any cost. Okay, to get breakaway at break in, both your k value should be a positive. Okay, there are some more some problems are there. For both the values of s, I will get k as a positive. That one is break in. That time we should go for detail. Hope screen is visible now.
Arun, Arun,
Sir, screen is visible.
screen visible,
Sir, screen
Arun.
visible இருக்கா?
It's not visible.
Ipo sir.
Now it's visible, Arun.
Okay, sir. Thank you. Okay. Sorry for the disturbance. So here, question number 11, they're given some root locus. They're asking which transfer function will give the exact one. Similarly, they ask something. Okay. So this is a given transfer function. Sorry, this is a given root locus. They're asking which one is the function for the corresponding figure. Okay. To check that, I can go for either centroid formula or I can go for any angle of asymptotes. But there is a longest procedure to find which one the correct transfer function. Instead, I can so take a point at s is equal to minus infinity and look towards the right side, okay, and count the number of poles and zeros. Okay, if the number of poles and zeros are odd number, I can say that system is that is a root locus. That is the transfer function of the root locus. Okay, once I am telling you, take a point at s is equal to infinity and count the number of poles and zeros towards the right side. Okay, and this is a condition for any root locus. If I see the option A, so the number of root locus are number of poles and zeros are even number. If I see the option B, the number of poles and zeros are odd number. If I see option C, once again even number, and option D is also even number. So obviously option B is the correct answer. The number of poles and zeros should be a odd number. I am telling you the count, not the values. Okay. Now, the 12th one, the natural frequency of an undamped second order system. Okay, if the system is damped with the damping ratio, it means that undamped is something but 40 radians per second. And what is the damped? So the damped natural frequency omega d is equal to omega n into root of 1 minus epsilon square. Omega d is equal to omega n root of 1 minus epsilon square. Omega n value is given and epsilon value is also given. That way you can substitute and find the value of omega d. That is a damped natural frequency. So here I'm getting 38.15 per second. And look into the black diagram. So when x1 of s is equal to 0, so the transfer function y of s by x2 of s, they're given 4 options. Okay. Here in the figure, x1 of s as well as x2 of s, they're feeding 2 inputs. At one point, if x1 of s is equal to 0, then this adder section will be eliminated. This will become direct short circuit. Okay. Under this condition, what is the transfer? The closed loop transfer function. That is the question. Okay. So just look into this figure. When x is 0, and this part will become the feedback for the of s. Okay. Now this 1 by s will act as a g of s, act as a h of s. It's very simple. Once again, the formula is g of s by 1 plus by 1 plus g of s into h of s. So that is a closed loop function. So output divided by input, y of s divided by x2 of s. Just substitute this 2 and find the values of your transfer function. So here I am getting s plus 1 divided by s into s plus 2, which is nothing but your option D. Okay. Once I am telling you, they given 1 of s as well as x s. So s will become the feedback for the next one. This will be h of s, g of s. Simply you can use the closed loop transfer function formula, g of s by 1 plus g of s into h of s. Next, once again the similar problem. They given LTI system. They given 2 equations, x1 dot and x2 dot. 2 differential equations are given. So having a value, a minus the initial state for us to find last. We can go for simple method of the options. So this is inverse Laplace of S into I matrix A whole inverse. So whole inverse. Si minus A whole inverse. Okay, and x of 0 is something with initial conditions. Here the initial conditions are 1 and -1. They mentioned that you can take it as a column x. Okay, so A matrix also they given, they directly given. Simply you can go for Si minus A. S is a variable into I is identity matrix. It's a 2 cross 2, so Si will become S0 0 S, and subtract with minus, subtract with A is nothing but -1 0 0 minus 2. Then if I get Si minus A is equal to S plus 1 0 0 S plus 2. Okay, we have to take the inverse for this, and we know the inverse formula 1 by determinant of A into adjoint of A. To find the adjoint of A, we'll do the interchange of two number two these two terms, and we'll go for sign change of this two. I think since there is 0, no sign changes. So the inverse Laplace of s plus 1 is e power minus t. Inverse Laplace of s plus 2 is e power minus 2t. So I got this CS. I have to multiply with x of 0. X of 0 is a column matrix. Just multiply. Then the final answer is minus e power t minus e to the power of minus 2t. This is the solution of your state for the given state equations. Another interesting one. So maybe in the next class I will completely focus on Bode plot. Now simply I given some clues. Okay, so based on these clues I'm going to start the next session. Okay, they mentioned some Bode plot here. Okay, so the system is connected with a unity negative feedback configuration. What is the steady state error of this closed loop system for a unit ramp input? Already I mentioned you. Whenever the given unit ramp, obviously we should get one system. Okay, if it is a unit type 2, then we should have parabolic input. If it is type 0, we should have unit step input. Okay, since I mentioned ramp input, we have to check the type of the system. But they didn't give any transfer function here, either closed loop or open loop. Nothing is mentioned, but they given Bode plot. Okay, from the Bode plot, we can able to identify the type of the system also. Okay, it is very easy. Start check beginning point, that is with respect to the frequency I'm telling you, not the magnitude. Okay, check the beginning frequency of your Bode plot. If the Bode plot starts with 0, okay, then your type of system is 0. Okay, if the Bode plot not starts with 0, okay, instead of 0 some other number, okay, 0.1 1 1.5 or 2 radians per second, if any numbers, then the type of the system is 1. It is not 0, damn sure. Okay, so in our Bode plot it does not start with 0, so obviously I can conclude that the type of the given system is 1. When the type is 1 and the ramp input is given, I can go for kV, that is velocity error constant. So here kV, how to find kV, that also is a very important one. Okay, when your Bode plot crosses your what is the x-axis or frequency scale, okay, that time check the corresponding value. Okay, so corresponding value is nothing but 2, so your kV is equal to 2. So simply I can take kV is equal to 2, and we know the formula ES is equal to 1 by kV. Simply they given A by, it's not so, it is, we can take 1 by kV also. Okay, maybe instead of unit ramp, if they give some other number, for example ramp with amplitude 2, then I should go for 2 by kV. Since it is unit ramp, I am taking 1 by kV. Since kV is equal to 2, ES is equal to 0.5. So the steady state error constant is 0.5. Okay, once I'm telling you, so here we have to find the type of the system. So since your Bode plot not starts with 0 radians per second, so the type is 1, and the value which is crossing your x-axis, that is your kV. So your kV is equal to 2. You can take both the values and substitute in the formula and get the ESS value. Okay. Now the next 3 to 4 questions is choice for the participants. You can answer directly. The pole factor is 1 by 1 plus j omega t as a slope of, okay, it is 20 decade minus 20 dB per decade or 40 dB per decade minus 40 dB per decade. Okay, so can you chat box? I will give a clue. There is only one j omega. Any B, that is minus 20 dB per d. In so once again, the option is to the participants. What is the pole factor of 1 plus j omega t? That's minus, okay. When then you will have plus whenever omega in the denominator will have minus 20. Okay. Since of 1 plus j omega t, so it is 1 by 1 plus j omega t the whole square. This your slope will be minus 40 dB. Okay. For each s or for each omega will have 20 dB. The 20 plus or minus depends on your position of that s. If s is placed in the numerator, then will have plus 20 dB. If s is placed in the pole's location, then will have the minus 20 dB. Okay. Hope you understand. For this, answer is minus 20 dB. Next. And this is also given to the participants. When gain of the open loop system is doubled, what about the gain margin? Any answers? The gain of the loop gain is doubled. What about the gain margin? That's a question they asked. Okay. Yeah, it's also very simple. Gain and gain are inversely proportional or reciprocal, I can say. Okay. So when gain is double, gain margin will be reduced by half of the times. When gain is increased by 4 times, your gain margin is decreased by 4 times, and so on. So, okay. Since the gain is doubled here, your gain margin it becomes half. Okay. I can always give the clue. It is nothing but T1 plus T2 divided by K into T1 T2. Based on this, your K is your gain, and this is the gain margin. Gain is double, gain margin decreased by half. The next one, 18th one, the closed loop system shown in below. Here we'll try to do a mistake. So we know that always we have a practice g of s divided by 1 plus g of s into h of s. This is a formula we'll always use. This is for a closed loop transfer function for negative feedback. But if I see this is a positive feedback. Okay. Since it is positive feedback, instead of plus I'll get the minus. Okay. So once again, g of s is equal to minus 2, h of s is equal to 1 by 4. And substitute this, I'm getting minus 4 by 3 as a closed loop system. And for a given system, rule is given below. The system may be stable or unstable, they're asking. So if I see the first column, one value is negative, that is minus 5. Simply I can say system is unstable. Okay. Sometimes there is a possibility of asking number of poles on the right side of S plane. Okay. Now there is no change from 1 to 1. There is no sign change from 1 to 1, but there is a sign change from 1 to minus 5. There is only one sign change. As well, there is another one more sign change, minus 5 to minus 5 to plus 7. So two sign changes. Since out of 4, okay, since it is S over 4, there will be 4 poles. Okay, 2 poles will lie on the right side of S plane, 2 poles lie on the left side of S plane. So system is unstable. Okay, the last one. So the open loop transfer function OLTF of a unity feedback G of S is given. What is the breakaway point of this? Okay, similar type of problem in the previous slides. They given GFS, they're asking the breakaway. Okay, we know the for breakaway by dA should be equal to 2. Okay, to find K value, go for characteristics equation 1 plus GFS into HFS. And from this we can find the value of K. So I'm getting K is equal to minus of S cube plus 3S square plus 2S. Differentiate this K with respect to S and equate to 0 and find the values of S. Okay. Your equation is after differentiated, The equation is minus 3s square plus 6s plus 2 whole minus 2 0. Then if I do the factorization of this quadratic, is 7, s is equal to minus 4, sorry, minus 0.422. If I see the options, both the answers are there, I think. So minus 0.42, as well as minus 1.57. So I think directly we can conclude there is no option for minus 1.57. You can neglect that. Simply you can take minus 4.22 as one of the shortcut. If not, maybe one of the option is, for example, one of the option is minus 1.577. That time we should go and check whether the first one is breakaway or second one is breakaway. We know the procedure to check breakaway. Take the values of S and substitute in the K equation and check whether K is positive or negative. If K is positive, that S value is a breakaway. If K is negative, that point is not breakaway. Okay, so I'm getting my take that value. I'm getting K is positive. So obviously that will be a breakaway point for this problem. Okay. Thank you. With this, I'll close the day. So the next class will be continued on the same topic on Wednesday, 11 o'clock. So mostly I will the Bode plot and Nyquist plot and polar chart. Okay. So with this I'll close. If you have any queries, you can unmute yourself and you can ask. Feedback form link will be posted shortly.
Sir, Arun sir, very good explanation.
Thank you, sir.
Okay, next time concentrate on that polar plot related problems. That is somewhat tough, if possible.
Sure, sir. Next time I'll focus on Bode and polar. And
the Nyquist plot, polar plot.
all three together I concentrate.
Okay. This session is very good. Very good explanation.
Thank you, sir.
Okay.
Any other queries? Okay. So the link will be posted shortly. Yeah, this is a feedback link for day 1. Praveen sir, please stop recording.
Thank you, Arun. Participant, please fill the feedback form. So after 15 minutes, the feedback form will be closed. Don't share this feedback form.
Sir, recording stop on it again. Praveen sir.